Question 4. Explain the decrease in atomic radius from sodium to chlorine. Absolutely routine, year 12 standard level question. As you go across a period, atoms get smaller, which is slightly surprising, slightly counterintuitive, because we've got more protons, more electrons, and more neutrons. But it's all to do with how tightly the electrons are being pulled towards the nucleus, right? So you have to, in your answer, make it really clear that the nuclear charge or number of protons increases. Number of protons increases as you go across a period, and you also have to state that you've got the same number of shells or same shielding, and it's the second mark that was often lost there. So same shielding, because it's no good having more protons and a greater nuclear charge if you've got 3 times as many shells, because that atom is going to be bigger. If you're comparing sodium plus and oxygen or oxide, so 2 minus, you have to explain why sodium plus is smaller than O2 minus. And again, we're thinking about numbers of shells, numbers of electrons maybe, and number of protons. Now, frighteningly, some people counted up the number of electrons in here and thought they were different and gave different values. And some people said the number of protons is the same, which is also slightly shocking, I have to say. But if you look at a periodic table, sodium, of course, has got 11 protons, and oxygen has got 8, but a sodium ion has got an electronic configuration of 2, 8, and an oxide ion has an electronic configuration of 2, 8. They have the same number of electrons, like all the other ions, either side of neon. So a nitride 3 minus ion has 10 electrons. So does this. So does this. So does this noble gas. So does this 1 plus ion. So does this 2 plus ion. So does this 3 plus ion. They all are what we call isoelectronic, and that's the first mark. But those isoelectronic ions around a noble gas, neon or argon if it's the next row down, gradually get smaller because you have more protons. So you'd say the isoelectronic, but you'd say that sodium has more protons, or has a greater nuclear charge, or something like that. The next question people found particularly challenging. So there's successive ionization energies of boron. So first of all, look up boron. It looks like that, and it's got 5 electrons, 2, 3, 2 in the first shell, 3 in the second shell, if you prefer, 1s2, 2s2, 2p1. Okay. So the first electron that's lost is this one, then these two, then this one. Now there will be a small difference between the ionization energies of the electrons that are being taken from P and S, but the difference between those is tiny compared to the energy required to remove the electrons from a 1s, which is much closer, much more tightly held to the nucleus, because they're closer to it. There's no shielding from it either, whereas these are all shielded by the 1s subshell. Okay, so the first, second, and third ionization energies gradually increase because you're removing an electron each time. And the first one you're removing from a neutral atom, the second one you're removing from a 1 plus ion, and the second one you're removing from a 2 plus ion, and so on. But to remove the electron from the 1s, it's going to take loads more energy, and then you're going to take a little bit more to get the last one off, again because it's now a 4 plus ion. Alright, so that's what you'd have to do. You can join these, you didn't have to join them, but you've got a mark for having them gradually increasing, or increasing as you go along, and you get a mark for having a big gap between here and here, so 2 marks for that. Again, pretty straightforward year 12 stuff that you just haven't remembered, some of you, or haven't revised sufficiently, I would say. Okay, so predict, given your reasons, whether Mn2 plus or Fe2 plus is likely to have a more exothermic enthalpy of hydration. Now, enthalpy of hydration appears not to be in your syllabus, but let's think about it very briefly. So entropy of hydration is the strength of the interaction between an ion and water that might be surrounding it. Okay, so we haven't talked about this much, which is why I don't think this question was given to you. I'm hoping not in the paper. I'm just going to check that. It wasn't given to you, so that's good news. But given they've both got the same charge, the strength of the interaction between them and a water molecule must be dependent, therefore, on the size, because electrostatics is all to do with either the charge or the size of things. And because iron 2 plus is smaller than Mn2 plus, for all the reasons we've talked about earlier on, there's going to be a stronger interaction. So that's got a more exothermic hydration enthalpy, but we don't need to worry about that then. At least I'm going to skip on. Is that it? That's it. Question 5. Right. If a reaction is homogeneous, it means everything is in the same phase as each other. So phase and state are almost interchangeable as words, still in the same state as each other. If you're interested in the difference between phase and state, look it up very briefly. You can have two liquid phases that are not mixing together, so they are immiscible even though they're both liquids. So they're not in the same phase, but they are in the same state. But anyway, they're homogeneous, these things, because they're all in the same phase or state as each other. Predict, given your reason, the size of the standard entropy change for the forward reaction. Right, so that's delta S, and you could calculate it using data from the data book, I guess, but you didn't need to do that. You have to predict it using information in the question. And you've got 3 molecules of gas. It's important you highlight their gases on the left hand side of the arrow, and you've got 2 on the right. So the delta S decreases because you go from 3 molecules of gas, or 3 moles of gas, also okay, to 2 moles of gas. 1 mark. Straightforward. Routine stuff you could literally all of you could do a few weeks ago. The next one, these get gradually more challenging. I think some of these are a little bit awkward. But question 5c, you have to work out the Gibbs free energy change for that reaction. But this first question was handled pretty well. You're given Kc in the question, which is up here. So the equation you're going to use is delta G equals minus RT natural log of K, or Kc, as given in the question. For that you'll need R. You look R up in the data book, it's 8.31, that's in joules per Kelvin per mole, so it's important to make a note of that, joules per Kelvin per mole. Be really careful because it's asking you here to give the data in kilojoules per mole. Okay, it's kilojoules, but it's the standard Gibbs free energy change, which is defined as 1 mole, isn't it? So plug the numbers in. Yeah, so it's minus 8.31. You're told the temperature at 1000 Kelvin. We've got to give the temperature in Kelvin. And then we're given the Kc, so it's the natural log of Kc, which is 280. You plug those numbers in, that'll give you the value in joules, which is minus 4.7 times 10 to the 4 joules. And so you just got to divide that by 1000 to give you the value in kilojoules. So delta G is equal to minus 47 kilojoules per mole. Kilojoules. Okay. Right. This was answered very well by some people, and I think others found it really difficult. So let me go through it bit by bit. Now, the best way I can think of showing this is by reminding you, of course, that delta G is equal to delta H minus T delta S. We were asked to think about whether the forward reaction is endothermic or exothermic, right? So we're going to be we need to work out essentially what delta H is. So delta H is equal to delta G plus, that's an S by the way, plus T delta S. Okay, delta G minus, it's delta H minus T delta S, or if you rearrange, delta H is equal to delta G plus T delta S. Now, we know that delta G is negative, we just worked that out, so that's negative. We know that delta S is negative, we've worked that out in the previous question. that term must be negative. So if you've got delta H is equal to a negative number, add a negative number, well, delta H must also be negative. So you'd have to say, to get the mark here, you had to say that delta G is negative, and you have to say that delta S was negative, just so that's what you're referring to. You have to say, therefore, that delta H was negative, and therefore the reaction is exothermic. Okay. I suppose if you had the earlier questions wrong, then there's a chance there might have been some kind of errors carried forward, but there's no clarity on that in the mark scheme, so I didn't give you a mark if you got everything wrong there. And actually, a reasonable number of you got pretty well there. Right, question E was again another slightly tricky one for people. So you were told a whole bunch of stuff about the concentrations of the reactants in this equation, right? But nothing in here does it tell you that this reaction had reached equilibrium at this point. It just tells you they're mixed together. So if you want to work out something called the reaction quotient, which is exactly the same as Kc, but before the reaction had reached equilibrium, you do the calculation you're comfortable with, you're familiar with. So it's the concentration of SO3 squared, because it's SO3 raised to the coefficient, which is 2, divided by the concentration of SO2 squared, again referring to the balanced equation over here, SO2 coefficient's 2, so raised to the power 2, times by the concentration of O2, and that gives you, that's what we call the reaction quotient. And that reaction quotient, if you plug those numbers in, comes to 20.8. You only get 1 mark for that, and you don't need to write down the units for that for IB for some reason, but there we are. So 1 mark for that. But then you had to consider whether this reaction would go in the forward or reverse direction. This is not well answered by you, or I think nationally when this was given as a question. But to decide whether a reaction is going to move towards products or reactants, you have to consider Q versus Kc. Now you were told Kc earlier on in the question, you were told it's 280. So our Q is less than 280, and that's important, and that's what got a mark. Okay, and you could get a mark by saying mixture needs more product for the value to equal Kc. I don't know, but I think just really clearly showing that Q is less than Kc is the important thing. So in order for Q to become the same as Kc, the only way that can happen, the only way that number can become bigger, is if this number goes up and these numbers come down, and that the only way that will happen is by the equilibrium shifting to the right. So equilibrium shifts to the right hand side. I'll stop there.